Hello, everyone. Today I'm going to be talking on the topic of AI automation in scanning electron microscopy on behalf of Amrita Academy. This is the list of the authors, which include myself. My name is Jeffrey Mahesh. I'm 17 years old. I'm from Milpitas High School, and next author is Dr. Biju Rao, along with ASDRP. So before I start talking on automation in scanning electron microscopy, I think I have to give a little background on what exactly electron microscopy is. Electron microscopy, or EM for short, is an imaging technique which uses a beam of electrons to visualize the surface topography / structure of relatively small samples which are far too small for a regular optical microscope, like the microscopes you find in your school science lab. To show how powerful an EM really is, its magnification ranges up to 1,000,000 times, while a school's microscope will go up to like 10 times. Within the subject of EMs, there exists a scanning electron microscope, or SEM for short. The SEM is unique in the way it produces high resolution and high depth of field images of a sample's topography in a raster or scanning method. The resolution of a basic SEM ranges from 1 to 20 nanometers. Magnification ranges from 20 times to 1,000,000 times, and it offers a large depth of field, up to several centimeters. Now, as unique as the SEM may be, it's actually quite common in the real world. One of the biggest car companies in the world, the Ford Motor Company, utilized the SEM in a study they conducted in the 1900s. The problem they were having with their cars at the time was a premature failure of transmission gears. And an SEM analysis revealed that they had microscopic cracks originating from inclusions and material inconsistencies. The outcome was that Ford adjusted their material specifications and their gear design. Similarly, General Motors had another issue with their own cars, and the problem they were having was a corrosion of their engine components. An SEM analysis revealed that they had pitting corrosion, which was caused by environmental contaminants, and the outcome was that GM eventually switched over to corrosive resistant parts for their important engine components. Now, as shown, the SEM is a powerful tool for identifying compositional points of weakness, which lead to amazing improvements in the field of metalworking and material science. But the slight issue with the SEM is that over a long period of time, it ends up being incredibly time-consuming for researchers to use. There are 4 essential parts of using the SEM. The first being sample loading. Second being microscope parameter adjustment, which involves adjusting 5 main parameters: focus, magnification, astigmatism, resolution, and beam intensity for researchers to locate and visualize their point of interest in the samples. Then comes the imaging process, which involves monitoring and fine-tuning to obtain high-quality images. And finally comes the sample unloading. Now, altogether, it seems kind of like a basic process, but over a long period of time, across days, weeks, months, and even years of doing multiple analyses on the SEM, it significantly impacts the productivity of researchers. It takes away a lot of time from their hands. So the solution we're thinking of is AI automation using machine learning methods. ML methods can be implemented to automate the imaging process, image interpretation, and eventually even full-scale experiments. We can get high-quality images in a quicker time. It'll significantly reduce researcher workload. As I said before, researchers spend up to days just trying to gain usable results from one SEM analysis. So AI automation will allow them to move their focus onto other complex tasks, while this will be essentially running in the background. So as we all know, the first step to building any AI/machine learning model is to gather data. So here is an image of the data set we've prepared. First column consists of the image ID, which represents which sample the different features were located in. Second column represents the feature type. We looked at 3 basic feature types: cracks, voids, and inclusions. And then comes the different parameters we adjusted: the focus, then the magnification, astigmatism, beam intensity, resolution, and finally we have the detection time. So the question we had to ask ourselves after collecting data was, what ML model are we going to use? We decided on the regression method, And to be more specific, we use the XGBoost regression model offered by Amrita's ML modeling system. And we decided on this because it's good for predictive modeling, classification, and ranking. Our current goal is to predict the detection time. And some questions we had to ask ourselves were, what factors affect the predictive variable? How does each factor affect it? Which factor has the greatest effect? Which factors do we have to take into account? And which factors can we essentially disregard or look over? Like, which factors has the least impact? Now, from the datasheet plus the XGBoost regression model, we found that the factors affecting the predictive variable are ranked as shown in the chart on the right-hand side. Focus has the greatest impact, then the beam intensity, then the magnification, then the resolution, and finally the astigmatism. And we learned that as the focus is greater, the harder it becomes to predict. As the focus is lower, easier it becomes to predict. And same pattern follows for beam intensity, magnification. But for resolution, the pattern switches up. As the resolution is greater, harder it becomes to predict. And as the resolution is lower, the easier it becomes to predict. With the astigmatism, there's not really a clear pattern represented. So this is the variable that we've determined that has the least impact on predicting the detection time. Now, out of the 4 other variables, we decided to focus on the focus and beam intensity, trying to automate these 2 first, since they have the most impact on the detection time.
I think what resolution is saying is, if I understand it, higher the resolution, shorter the time to find the feature you're looking for. So red means higher, right? Blue means lower. So negative sharp value means it's lower, lower time to detect it, right? Which makes sense. So,
Right.
Yeah.
So our future plans include integrating the AI models with the SEM software by using coding. We're most likely gonna stick with Python. And then after that, we need to work on testing and optimization. We need to monitor and make sure the AI system performs reliably and produces the expected results. One question we have to ask ourselves is how many hours of testing is really necessary? We need to continuously refine the models with new data and new feedback. And eventually, we hope to start researching into robotics, to start automating the loading and unloading processes, since those 2 processes are the only physical parts. But this most likely won't be until much later in the project, since we're currently focusing on the imaging process. Thank you all for listening. Feel free to ask any questions.
Yeah, very good research. I see you using XGBoost, which kind of decision, which is not a neural network. Are you looking at also potentially using the transformer model or some generative architecture, deep learning to do the image processing?
Yes, that'll be sometime in the future. It's a new project we just started, so this is just the basics of what we covered.
Like, yeah, right. Sometimes even traditional ML method still works. Right. Thanks.
Yeah, thank you. Oh.
That's a wonderful project also. Do you think the results are going to be dependent upon the type of material that you're looking at? And will you need a much bigger data set and categorize it by material type?
Yes, we will in the future, but right now we don't have access to a lot of materials. We have like 3 basic samples, which is where this data set came from. But yes, eventually in the future we will need a lot more.
Thank you. Very good project also.
Yeah, I think your affiliation with that other funded research is also good, right? You have a team working there.
Yes.
Are you guys looking into applications beyond automobiles, like maybe into like Boeing quality control processes and things like that? Because those problems, if we can detect early, then they can be remediated early, right? Are those kind of applications also in your research scope? Or?
Yeah, they are sometime in the future.
When you are in college.
Yeah, most likely. Yeah, because this is a very like, diverse field.
Right,
So, yes.
right. A lot of
There's
possibilities.
a lot of use cases
What was your inspiration?
for this project. Oh, well, I joined another nonprofit organization, and this was one of the projects they offered, and I thought it was interesting because, well, AI is like a rapidly rising field, and so I thought it would be a cool project for me to work on. Thank you.